Okay, hello everybody. Continuing on in chapter 2.5 here, measures of position, Mat 235. I want to talk a little bit more about how we use that empirical rule when our data is indeed normally distributed or bell-shaped. Remember that bell-shaped distributions are also called normal distributions, and we use this to refer to any set of data that is more or less symmetrical about the mean. So again, what that means, if I draw a continuous line over these histograms, I'll see my curve looks like a bell, and what that means is that the data is clustered around the mean and is falling away in decreasing frequency from that mean symmetrically as I go above and below. And this is a very popular shape or distribution of our data that we see in this course. And what we talked about last time was the 68, 95, 99.7 rule, which tells us that when our data is indeed normally distributed, and it only works for bell curves, do not forget that we can use this table here, or not table, but graph rather, to determine what percent of our data will fall between these various ranges. Ranges going from 3 standard deviations below the mean to 3 standard deviations above the mean. And outside of those range, well, not much data at all will fall beyond 3 standard deviations. This is the other thing to take away from this rule. If I go 4 standard deviations away from the mean, well, there's only 0.3% of the data left that could even be that far away from our average. So let's do an example here just to see how we can use this rule. We'll start with a very simple example. We'll take IQ scores for this set of data because they're nicely arranged so that the mean IQ for persons is 100 and the standard deviation is 15. So if I were to ask you a question like what percentage of people have IQ scores between 70 and 130, well, since this data is indeed normally distributed, and it's known to be, but we can also see from our graph here that the data seems to be approximately normal, so we can use the 68, 95, 99, 7 rule. And in order to use it here, we just need to look at these two scores and look at a score like 70 and ask yourself the question. It's an important question to be able to ask yourself. You should sort of think this anytime you see a data value in this course. How many standard deviations above or below the mean is this? How many standard deviations above or below 100 is 70? And so what I mean is if I take 100, how do I get to 70 by adding or subtracting 15? Well, of course, 15 times 2 is 30, and 100 minus 30 is 70. 70 is right here. And so what this means is that the number 70 is exactly 2 standard deviations below average. Okay? And similarly, if I look at 130, the same calculation will tell me that 130 is 2 standard deviations above average. So what does that mean? That means that this question here that's being asked to you, what percentage of people have an IQ between 70 and 130, is just a rephrasing of what percentage of people in this set have an IQ within 2 standard deviations of the mean. There's no difference between me asking you what percentage of people have an IQ within 2 standard deviations of the mean, and in this example saying what percentage of people have an IQ between 70 and 130. They mean the same thing. And so that's how I use the 68, 95, 99.7 rule, because I know that this rule tells me within 2 standard deviations of the mean, that's from 2 standard deviations below to 2 standard deviations above, I will always find 95% of my data. And if I add up these 4 numbers, 34, 34, 13 and a half, 13 and a half, you'll find it adds up to exactly 95%. So the answer to this first question is that according to that rule, the empirical rule, or 68, 95, 99, 7 rule, approximately 95% of people should have IQs between 70 and 130. And so along the same lines, using the rule in sort of the very same manner, remember I could have also used this to determine, suppose that instead of saying between 70 and 130, I asked you for the percentage of people who have IQs between 85 and 115. All you would have to do is recognize that this means exactly one standard deviation away from the mean. So how many people, what percentage of people have IQs between 85 and 115? That would be 68. And if I extend it to 3 standard deviations away from the mean, that would be IQs between 55 and 45, 145. Then that would be 99.7% of people. And so, like I mentioned last time, don't forget that because these curves are symmetric, I can say a little bit better than just 68% of people are within 1 standard deviation. I can say that 34% of people are between the mean and 1 standard deviation below. I can say that if I take these two here, 47.5% of people are between 2 standard deviations and the mean, and so on and so on. Any way that I can slice up a normal distribution on these barriers here, I can use these percentages to figure out exactly what percentage my data should be between these ranges. So as one more example, let's look at SAT scores. So the mean score for SATs, we'll take it as 1026, and the standard deviation is 200. So for example, Howard Stern, you may recognize Howard Stern from America's Got Talent. Is he a smart guy? I don't know. Let's see how he did on his SAT. He scored an 826 on his SAT. So given that information and given that the mean is 1026, the standard deviation is 200, what percentage of people would you say scored higher on their SATs than Howard Stern? Think about this for a second and see if you can come up with an answer. So, how do I find what percentage of people scored higher than Howard on their SAT? It's always important. Please read the question carefully before you start to answer it. And so what I'm asking you here is that if I looked at the distribution of all possible SAT scores, then let's find where Howard is. Howard would be right here. The mean is 1026, and I know that Howard scored exactly 1 standard deviation below average. How do I know that? Because, well, his score just happens to be 200 below the mean. 200 is the standard deviation. So, the empirical rule tells me, here I'm not really looking, well, I am looking for a range. A rephrasing of our original question is, what percentage of SAT takers were in this region that I'm shading right here? What percentage of SAT takers were above 826? That means what percentage of them scored from 826 to 1600? So how can I find this range? How can I find this range accurately? Well, all I need to do is sum up all the portions of my graph that are actually above Howard Stern's score. So in this case, I know that the empirical rule tells me that this is 68% right here, and it tells me that this portion is 13.5. That's half of the way to adding me up to 95%, and that this portion here is 2.35. So if I sum all of these values up, I can get an estimate saying, well, about 84% of people probably scored higher than Howard Stern. And if I was really being picky here, I could actually remember that there's an extra 0.3% here that falls outside of 3 standard deviations. So I could go ahead and add in a 0.15 to this number, but since we're estimating it, I would still probably round that off to 84% in the end anyways. And so one more example for today, just give this one a shot. Let's assume the same mean and standard deviation of SAT scores, the mean 1026, the standard deviation of 200. The average SAT, and this is true data, the average SAT score of somebody who's admitted to Notre Dame University is 1426. So what percentage of students do you need to score better than on your SAT if you want to have an SAT score that's equal to 1426? If you score 1426, what percentage of people have you beat? Think about that for a second, and I'll tell you the answer in a minute. Okay, and so how do we answer this question? Well, once again, it comes down to just looking at sort of the distribution of this data and using the empirical rule. So because we know it's bell curve and we know that our score in this case, 1426, is of course a nicely selected point of data because it equals exactly 2 standard deviations above our mean of 126. So here, all I need to do is say, well, what percentage of my data is in this red shaded region that I've half shaded here? From 1426 and below, how many people did I beat when I scored a 1426? And there's two ways to do this. One way, of course, is just to go ahead and add up all the percents that happen in these regions below. So I can take my 2.35 percentage of people, which is 3 standard deviations below. I can add the 13.5 percentage of people who are between 626 and 826. I can add 34 and 34, which I'll do in one calculation, to give me the 68 percentage of people that are between 826 and 1226. I can hardly read my own writing. It's tough writing with this stylus. And the 13.5 percentage of people that are from 1226 to 1426. And I can add all this up and find what percentage of people approximately were below me. And I could also add up that other 0.3%, which I probably should do here. Of course, the other way to do it is to know that 100% of my data should be everybody underneath this entire curve. So, and this is a good idea and good practice, if this whole curve represents 100%, and this section here represents 2.35%, then what percentage is the red shaded region? Well, it should be 100 minus 2.35. And this is a little bit of an easier calculation, right? If the entire region, red and blue, equals 100, then 100 minus red equals 100 minus blue, equals red. So another way to do this is just to do this simple subtraction here. 100 minus 2.35 would give me something like 97.65. And if I was being a little more precise, although because this is a game of estimation, I would also include this 0.15 on either end here and here. But in any case, it comes out to be approximately the same number. In the end, the conclusion that we should make is somewhere close to 98% of my data is below 1426. And if you add up all of these numbers, you'll get approximately the same answer. So we'll say about 98% of all SAT scores fall below 1426.